Hi everyone, my name is Caitlin Frobotnik, and I am a conservation agronomist for the Natural Resources Conservation Service in New Jersey. My job is to protect resources across New Jersey and to find ways to help our producers to be better stewards of the land. Working for NRCS, we have defined resource concerns and planning criteria. We have 31 different resource concerns that we must consider as part of our planning process. That means that there's 31 different things we have to look at every time we go out to a site. Now, for us, a site could be a particular field that a producer is having issues with. It could be an entire farm. It could be just the farmstead area of the farm. The site is really determined by the planner and the producer. Now, if you look at the list of resource concerns, you'll see soil erosion, soil quality degradation, excess water, insufficient water, water quality degradation, degraded plant condition, inadequate habitat for fish and wildlife, livestock limitation, inefficient energy use, and air quality impacts. In parentheses behind each of these resource concerns, there's a couple numbers. Soil erosion, for instance, has three main categories. Sheet and rill and wind erosion is one category. Concentrated flow erosion is another category, and stream bank erosion is another category. But then we have, for concentrated flow, ephemeral gullies and classic gullies. So we really have three different types of soil erosion that we're looking at when we're looking at the soil erosion resource concern, but there's four different ways to assess that erosion, four different tools that might be needed, four different criteria if erosion is actually a concern or not. Soil quality degradation has four resource concerns associated with it, and excess water only has one, but under excess water we have ponding and flooding, we have high water table, seeps, or drifted snow. Those are all subcategories of excess water that need to be looked at every single site. So we really have more than 31 different evaluations at every site, but we have 31 main categories that we look at. Whenever we go out to a site, our first goal is to identify which concerns exist, and we want to identify what the producer objectives are. Now, some of these resource concerns are obviously related. Soil erosion, soil quality degradation, and water quality degradation are very closely related. If we have soil erosion occurring, there's a good chance that we can have water quality degradation occurring also. Through the process of soil erosion, we might end up with sedimentation in any surface water bodies. We might end up with nutrients, pathogens, pesticides in those surface waters. And obviously soil erosion and soil quality are very closely related. The more we have soil erosion occurring, the more our soil quality goes down. So every time we lose topsoil from soil erosion, we're going to be degrading the overall health of our soil. Some other ones that may not seem so related, but are still related, include soil quality degradation and excess water. One of the issues that could happen with excess water is that we could have ponding. Now, ponding can occur because of inherent properties, or it can be related to more dynamic properties, which we'll talk about a little bit later. If we have poor infiltration, we can have ponding occurring. We might have poor infiltration because we have poor soil quality, or because we've had a lot of erosion. Degraded plant condition is another one that can be related to soil quality degradation. With plant condition, obviously, a lot of the resources that the plant needs comes from the soil. So if we don't have healthy soil, we're not going to have healthy plants either. The process of soil erosion is caused by detachment, transport, and deposition of soil particles. Understanding the process of soil erosion is really important to be able to treat the soil erosion. The process of soil erosion often first begins when we have rain droplets that impact an unprotected ground surface. When that impact occurs, it will detach soil particles from the soil structure, and then these particles can be moved into a transport and will eventually be deposited somewhere on the landscape. Understand this process is really important to be able to treat erosion. If we can control soil erosion at the detachment stage, we're preventing transport or deposition from occurring. Practices that can minimize detachment include practices like reduced tillage or no-till, which means that the crops are planted directly into the residue of their previous crop or cover crop. No plowing, chiseling, or disking occurs with a no-till system. Other practices may include cover crops or critical area planting. Really, any practice that maximizes the surface cover in the field will help minimize detachment. And this works because the rain will hit the leaves of the cover crop or the residue in a no-till field instead of making contact with the soil particles. Transport is the next process of soil erosion. Once the particles become detached from the structure, they can be transported. The amount of transport depends on the surface cover, the slope, and the slope length. Longer, steeper slopes will yield more transport than flatter, shorter slopes. During transport, not only are soil particles transported, there is a risk of pathogens, pesticides, and nutrients being transported if they're attached to the loose soil particles. Anytime we can shorten our slope length, we can limit the amount of transport because the momentum of the water is slowed down or completely stopped. Practices that help with minimizing transport include practices like contour buffer strips or strip cropping. These practices are planned within the slope of the field and will slow or stop the momentum of the water at certain points within the field. For example, if we have a slope that's 150 feet and there are no best management practices in that field, if detachment occurs at the top of the slope, we might get transport for the whole 150 feet and then deposition at the bottom of the field. If we put one contour buffer strip in that 150-foot field and we put it mid-slope, we're reducing the slope length of that field from 150 feet to 75 feet. We've minimized the length that transport is occurring. We've controlled where deposition occurs. And when the soil and water hits that buffer strip mid-slope, it's going to slow down and momentum will have to start again on the other side of the slope. So instead of having uncontrolled erosion for 150 feet, we're stopping that erosion at 75 feet down, and then the erosion process will have to start all over again. Once the momentum of transport is stopped, we have the third process called deposition. Deposition occurs when the slope either flattens out or when the soil particles are trapped by vegetation. One goal is to change where deposition occurs on the landscape. If deposition occurs in a stream, it's called sedimentation. Once we have sedimentation, we've moved from only having a soil erosion and soil quality concern to having a water quality concern also. Practices that control deposition include filter strips, repairing buffers, or vegetated treatment areas. The risk of only planning a practice that controls the site of deposition is that if the practice fails, you'll have uncontrolled erosion, which may impact other resources such as water bodies. The best way to control erosion is to plan practices that reduce all processes of erosion. That way, if your practice that you plan to control detachment fails, or the practice that you plan to control transport fails, you have the other two processes of erosion still controlled. Our agency has always addressed soil quality degradation, but addressing soil health is something that our agency has recently been really studying and focused on. The soil health is really important to address because the health of the soil affects so many other functions in our ecosystems. There are 5 vital functions of our soil. Regulated water is one of the vital functions of our soil. The soil will help control where rain, snowmelt, and irrigation water goes, and water and dissolved solutes will flow over the land or into and through the soil. Having healthy soils can actually reduce the amount of flooding that occurs on a landscape. Another important function, obviously, is sustaining plant and animal life. The diversity and productivity of living things depends on the soil. If we have a soil that has poor quality, if our pH is low in the soil, have poor soil structure, or if our biological diversity in the soil is very low, then we're not going to be able to produce and sustain as many plants or animals as a healthy soil would. Another important function of our soil is filtering and buffering potential pollutants. The minerals and microbes in the soil are responsible for filtering, buffering, degrading, immobilizing, and detoxifying both organic and inorganic materials, which include industrial and municipal byproducts and atmospheric deposits. Soils are very good at controlling pollutants, but you need a healthy soil in order for this filtering and buffering process to work. If you have an unhealthy soil won't have the ability to filter or buffer pollutants as well as a healthy soil will. An important part of being able to filter and buffer pollutants is to allow as much soil-water contact as possible. If you have a soil that has poor infiltration, or if you have a soil that's compacted, that water won't be able to move through the soil. On the other side of things, if you have a soil that's too porous, that has very low water holding capacity, and has a high leaching potential, any pollutants that are included in the water can move through the soil very quickly, and they won't have the chance to be filtered or buffered out. Cycling nutrients is another very important function of our soil. Obviously, the most important nutrients for crop production be nitrogen, phosphorus, and potassium, but we also have a lot of micronutrients that are cycled through the soil, and the soil will also store and transform nutrients. And last but not least, the physical stability and support of the soil is a vital function. The soil structure provides a good medium for plant roots, but it also provides support for structure and can protect cultural resources. When we're thinking about soil health and quality, there's three main categories that we think about. There's the chemical, the physical, and the biological. Physical properties could include aggregate stability, water holding capacity, infiltration, and soil structure. Chemical properties can include electrical conductivity, soil nitrate, soil pH. Biological properties could include particulate organic matter, soil enzymes, the amount of soil respiration occurring, which is a way to measure and estimate the amount of microbial activity in the soil. So when we're talking about soil health, there are 4 key principles for improving soil quality that our agency stands by. Manage more by disturbing less is the first one. This means that we want to disturb the soil as minimally as possible. Oftentimes when we go into a system where we're disturbing the soil less, there's other factors that come into play that affect our soil health, our soil quality, and ultimately our production. For instance, soil pH, we correct low pHs with lime. If we're disturbing the soil less, that lime's not going to be able to be incorporated as easily as if we were tilling the lime in every 3 years. So for a producer that is working to not disturb their soil, they have to monitor their pH values a lot more closely than a producer that is disturbing their soil, because you're not going to be able to incorporate that lime like you could for a soil that's being tilled every year. When you disturb your soil less, you really have to be proactive to make sure that your soils remain productive, because you don't have the opportunity to be as reactive as you can in those situations because you're limited by the amount of disturbance that you can cause to the soil. Another key principle is diversifying soil biota with plant diversity. So each type of plant grown in a field has specific microorganisms that will grow along with that plant. For instance, in a wooded area, you're going to have a lot more fungal species than you would in crop field where you have a lot of bacteria. So if we can grow different types of plants in a field, and whether those plants are grown together, such as in a cover crop mix, or grown in succession like in a conservation crop rotation, we're going to improve the number and the amount of microorganisms we have in the soil. Maximizing the diversity of microorganisms in your soil will make your soil more resilient and more adaptable to different crops and different climates. Now the next two are pretty similar. Keep a living root growing throughout the year and keep the soil covered as much as possible. Keeping a living root growing throughout the year will ensure that you always have biological activity within the soil. And that's important because you want to keep your microorganism populations up. Keep the soil covered as much as possible is another key principle. This can be done by growing something all year long, which would feed into the third principle there, keep a living root growing throughout the year. But we can also achieve this fourth principle by using reduced till or no-till methods, where we have high amounts of residue left on the soil when the main crop comes off. So if we harvest a corn crop, we're going to have a lot of residue on the soil, and we want to keep that residue all winter long. We want to keep it in the spring, and we want to plant right into it. This will minimize the soil erosion happening on the site. There's two different properties that need to be considered when planted. Soils have both inherent and dynamic properties. Inherent properties are properties that the soil retains from the soil forming process. These properties are not able to be changed on the human time scale, so within our lifespan. An example of an inherent property is soil texture. The soil will get its amount of sand, silt, and clay from the processes in which it was formed. Dynamic properties, on the other hand, can be changed by management practices, and they can be changed within the human timescale. Dynamic properties include organic matter, soil moisture holding capacity. We need to respect the inherent properties of the soil in order to plan successfully. We cannot change these properties, but we can mitigate for them if they are an issue. If we're working in a soil that is inherently sandy, we must understand that sandy soils do not have the capability to hold water like silt or clays. However, there are practices that we can use that will help to mitigate the inherent properties of the sand. If we're working with a producer that's concerned with the amount of water they're using to irrigate the crops, we can plan practices that will help increase the moisture holding capacity of the soil. We do this by increasing the organic matter and the content in the soil. Practices that we could recommend include cover cropping, mulching with leaves or compost, and using reduced till or no-till practices. All of these practices add organic matter to the soil. Using reduced till or no-till methods not only adds organic matter to the soil, but also limits the amount of evaporation of water from the soil because the soil is covered, reducing water losses to the atmosphere. To conservation professionals, if these practices are implemented, there are environmental benefits of reduced erosion and possibly better groundwater quality because of the additional filtering that will occur from the water not leaching through the soils quickly. To the producer, we sell these practices as ways they can save money. If they increase the water holding capacity of the soil, they won't have to irrigate as much, which means lower fuel costs of running their pumps. If the irrigation source is unreliable, such as an older pond, then we're also ensuring the crops will have a better chance of maintaining growth in the summer months because of the increased water in the soil. If the pond went dry and there is no water to irrigate, that producer may be facing stunted growth during those summer months or a complete crop failure. Another example of an inherent property that can affect the use of the land is depth to bedrock. If a producer wants to grow a crop on a soil that has a shallow depth to bedrock, we can work with them to find appropriate crops to grow. Since we're not going to be able to change the depth to bedrock and we cannot build enough soil to make an impact on that property within the human timescale, we must find ways to mitigate the issue. We might plan a crop rotation on the site that includes only shallow-rooted crops, but we also have to remember that with shallow depth to bedrock, sites are often very droughty or it can be very wet. So we'll have to examine the site to determine if we need to include crops or varieties in the rotation that like either dry or wet feet if we do have an issue with droughtiness or wetness. We have a lot of tools that we use to determine our resource concerns and to predict how well any of our best management practices will affect that resource concern. Some of the more important tools that we have is our Russell 2 program. Now Russell 2 only assesses water erosion. We have a different program to assess wind erosion, and Russell 2 only addresses sheet and rill erosion. So gully erosion and mass waste in events such as a landslide are not addressed or are not evaluated in the Russell 2 program. Other things that are very helpful include aerial photographs, topographic photographs, and of course soil maps. Along with the soils maps, there's also a lot of very important soil survey information that can be used to determine site capabilities and limitations. Farmland capability class is one of the most important interpretations we look at. Russell 2 considers many different inputs and considerations. Our outputs that we get from Russell 2 are only as good as the inputs that we use for Russell 2. Some of the things that affect our Russell 2 results is the climate. How much rainfall do we get and when do we get the rainfall? The soils obviously affect the amount of erosion that will occur. silty soils erode at much higher rates than sandy soils or clay soils. Our management is something that we have to include, which will include the crops, the yields, any dates of planting, harvesting. We include tillage that occurs and the number of times that tillage occurs. We also include manure or mulch applications. And slope length obviously are very important. Our steeper slopes are going to be more erosive than our flatter slopes, and our longer slopes are going to be more erosive than our shorter slopes. Our soil T-value is a constant for the type of soil, and any supporting practices are also included in Russell 2. So if we have any diversions, filter strips, or if we're contour farming, all of those practices are considered in Russell 2. So some of the important outputs we get from Russell 2 is our plan soil loss value. This is the soil loss that occurs within the field, and every soil has a T-value, and we can find out from Russell if we are under that T-value or over that T-value. We want our rotation and our management to give us a soil loss that is below the soil T-value to be sustainable. Sediment delivery is another output that we get from Russell 2. If we include a filter strip or a buffer strip in Russell 2, Russell 2 can calculate not only the amount of soil loss that's occurring on the field, but it can calculate the amount of sediment that's expected to be delivered off the field. The soil conditioning index is very important. The soil conditioning index is either positive or negative, and if it's a negative value, the soil organic matter levels are predicted to decline. If it's a positive value, the soil organic matter levels are predicted to increase. So our soil condition index, which we call SCI, can tell us if that rotation is expected to increase or decrease the organic matter in the soil. This doesn't give you the exact value of the organic matter, but you can tell if it's a negative or positive trend in soil organic matter levels. The STIR value, which is the soil tillage intensity rating, is another output that we get. This utilizes the speed, the depth, the surface disturbance, and the type of tillage that is used for that management system over that rotation. The kind, severity, and number of ground disturbing passes are evaluated for the entire cropping rotation. If you look at the table on the slide, you can see that each management that occurs in the field has its own STIR value. So our chisels with the twisted shovel have a STIR value of 46. The higher the STIR value, the more disturbance that management creates. So if we're comparing our chisel, which has a STIR value of 46, to our disc, which has a STIR value of 33, we can know that our chisel has a higher amount of disturbance than our disc does. And lastly, fuel use is something that we can also calculate. We have to add in our type of fuel and the cost of the fuel, but we can compare the fuel use of different managements and different rotations. This slide here has an example of a Russell 2 printout. Russell 2 is only a planning tool. We must field verify that the practices that we're planning will work on the site, and we have to field check any implementation that occurs. Just because Russell 2 says that adding contour farming and a buffer strip is going to reduce erosion, we need to go out to the site after those practices are implemented to make sure that we're actually getting the erosion reduction that we need to get. Now if you look at this printout, there's 3 different charts. The first chart just has the owner name, the location, and the tract and field info. The next chart has your field name, your soil type, your slope T-value, and the length and the slope steepness. Now, the slope length and the slope steepness comes from data that's collected at the field and is input by the user. The slope T-value is a constant that every soil has. That value is the amount of soil that can be lost in tons per acre per year and still have a sustainable system. The third chart that you'll see includes the field name, the description, and then the chart continues to show if you have any contouring systems added, if you have any support practices, if you have any terraces or diversions. Your cons plan soil loss in tons per acre per year is the amount of soil loss that's expected to be lost from the site using that specific rotation, management practices, and BMP. And then you can see that your soil conditioning index and your stir values are also listed here along with the fuel cost. Now we want to make sure that our cons plan soil loss is less than our slope T value. Now this particular site has a T value of 4. Only that last rotation with those BMPs added gives us a soil loss that's less than 4. And this last management has a lot of best management practices included. I'm not sure if any producer would want to do all of the practices that are listed here. We have contouring, we have 2 grass buffers, and we have a diversion on that site. That may not be practical on our site that has a slope length of only 150 feet. So we may want to look into changing the tillage on the rotation rather than trying to reduce our soil loss by adding best management practices. Aerial photographs are extremely helpful in looking at a site. Not only will aerial photographs give you a look at the site before you go and visit the site, but looking at historic aerials can give you a timeline of the managements that occurred on that site, any problems that occurred on that site. You can figure out if those problems were historic or if they were new. And I always say that the old timers knew what they were doing. Typically, if there is a hedgerow in a field, there's a reason there's a hedgerow in the field. If there's a tree in the field, there's probably a reason there's a tree in the field. One of the sites that I use a lot is Big Maps. They have that bird's eye view where you can get very, very detailed aerial photos of a site. Historic Aerials is a really good site that will let you look back in time at a particular site. The historic use of the land is important for planning because you'll be able to see what the historic problems were for that site. You can also identify when a problem began and the possible cause of that problem. Once you've identified the source of an issue, you can work on finding solutions. This is an example of a snapshot from the Historic Aerials website. You can see on the left, I have an aerial photograph pulled up from 2013. And on the right, I have an aerial photograph pulled up from 1953. Historic Aerials will also let you compare historic topo maps. And in this case, you can see some erosion happening on the lower right side of the field. When we pull in the historic topo map, we can see the area where the erosion occurring is a natural drainage area. And this lets us know that to address this problem, we'll really need a best management practice that's capable of stabilizing a drainage area, such as a grassed or lined waterway. Since we can't change the topography of a site, we must work to mitigate the issues that are recurring using best management practices that are capable of the current site condition. We talk a lot about the information that we get from soils maps and the soil survey. And the official version of any soil survey is on the web soil survey. Previously we had soil survey books, and those are no longer official versions of soil surveys. The web soil survey has the updated soils information for every county and the updated interpretation. One of the most important interpretations that we use is farmland capability class. This groups soils into 8 different categories. There's an irrigated and non-irrigated capability class interpretation. In New Jersey, we mostly only have non-irrigated capability class interpretations for each soil. Class 1 soils have slight limitations that restrict their use. These are the most productive soils in the country. Generally, they're deep, tillable, they're flatter, they're floodplain-like areas. The only practices that should be needed on these sites are conservation practices that would be needed to maintain fertility and soil structure. Practices might include nutrient management or cover cropping. Class 2 soils are generally easily farmed soils. They're more prone to erosion than Class 1 soils, and they have greater slopes than Class 1 soils, but they are still very productive soils and important for the farming industry. Practices that may be needed on these soils are practices that reduce erosion, such as contour farming or residue management. Class 3 soils are moderate soils. They're steep sloped. They often suffer from erosion or rainfall irregularity. They're inherently low in soil fertility, And these soils really need adequate plant cover for erosion and to maintain structure, and they often require drainage. Class 1 and 2 soils are soils that are the best for farming. Class 3 soils do have limitations, so we really want to be growing minimally intensive cropping systems on our Class 3 soils. These soils are best suited for hay production, pasture production. Once you get to Class 4, your soils really aren't suitable for cropland anymore. Our Class 4 soils, they're steep sloped, they're often deficient in water, they're very erosive, and they're low in fertility. They're not suitable for production in agriculture. You're going to have a lot of best management practices in place in order to make Class 4 soils suitable for production. Class 5 soils are often foothills or mountain valleys. They're mostly wet and stony. Again, they're not suitable for crop production, but they're not very erosive because they're mostly flat areas. Class 6 soils are steep, shallow soils. Once you get into Class 6 soils, you really don't want to be grazing them anymore. Class 4 and 5 soils are best suited for pasture land, forest land, or wildlife. Class 7 soils are really poor for grazing and forestry. Again, they're also steep and eroded. They can be shallow or swampy. Class 8 soils are miscellaneous areas that have severe limitations that restrict their use. Now, every capability class can have a subclass, except for Class 1. Class 1 does not have any subclasses because Class 1 soils don't have any limitations. The subclasses let you know what the restrictions or limitations on that soil is. So you could have a soil that's a 2E. That means that it's a farmland capability class of a 2. It is susceptible for erosion. Soils that have a subclass of E means that they are very susceptible to erosion, and past erosion damage. Sub-capability class of W means that there is poor soil drainage, wetness, or high water table. In some cases, this can be corrected by artificial drainage, but not always. Sub-capability class S is made up of soils that have limitations within the rooting zone, such as low fertility or high salinity and sodium content. And sub-capability class C are used in only some parts of the United States where climate is a limiting factor. So we might have a super high, super low temperatures, or very high or very low rainfall, which affect their use. This is an example of where these classes normally lay on the landscape. You can see our Class 1 and our Class 2 soils are the most productive areas. And here's another view of some soils on a landscape. Other important soil interpretations include the depth to restrictive layer, drainage class, ponding and flooding frequency, depth to water table, soil erodibility, and obviously your T factor. So when choosing a BMP, we must first identify what the problem on the site is, and then we have to identify how that problem is happening. We also need to consider what the capabilities of the site are, and that includes the management abilities of the producer. If we're going to be recommending somebody no-till a field, but they don't have no-till equipment, that's not a very good recommendation to make because it's not able to be implemented. If we're recommending to plant a hedgerow to minimize pesticide drift and reduce wind erosion, we have to figure out if the site is capable of supporting that hedgerow. If there's a shallow depth to bedrock on the site, most likely a hedgerow is not the best option. Our list of BMPs and their associated documents is located on the Electronic Field Office Tech Guide. We call it the EFOTG. When you first click on the EFOTG, there will be a map of the United States. You want to click on New Jersey. It'll come up with a map of New Jersey, and you want to click on whichever county that you're in. And you want to navigate to Section 4 and open the folder that says Conservation Practices. The entire list of BMPs that New Jersey offers through NRCS is listed here. Every practice has a standard that lays out the appropriate site and purpose for that standard, as well as guidelines for what should be done to meet the standard. Many standards have accompanying technical references that will help a planner determine how to make recommendations for that standard. For instance, the cover crop standard has a technical reference which lists all the cover crops that NRCS recommends for New Jersey, when they should be planted, and at what rate they should be planted. So our role as a federal government agency is really to help the producers help their land. All of our work that we do with the producers is voluntary. We don't regulate any state laws. We don't regulate any federal laws. We work with the landowners to identify their resource concerns and recommend potential best management practices to address those resource concerns. And producers may be eligible for financial assistance through farm bill programs that we administer. Another role that we play as NRCS is we also purchase easements to preserve farmlands and wetlands. And we have a lot of partners that we work with. We have partners from other government agencies, and we have partners from nonprofit agencies. This really allows NRCS to collaborate with other agencies to maximize the knowledge of their employees and the resources that we have to offer and that they have to offer. I know this was a really quick overview of some of our planning process, how to identify resource concerns and best management practices, but if you have any more questions, feel free to contact me.